Now we have our analysis question. And what do we know? Rectangle WXYZ represents one whole unit which has been divided into 7 smaller parts. These parts are labeled A, B, C, D, E, F, G. Copy and complete the table stating what fraction of the rectangle each part represents. So what do we do? To find the fraction that each part represents, divide the area of each by the total area. And of course, the total area is a rectangle 3 units by 12 units. There we have the entire area 3 by 12 units. So the area of the total A sub t is 3/12 36 units squared. Part A is a square of side 3 units. So its area is 3 times 3, that is equal to 9. And of course, the fraction that represents is 9 divided by 36. Of course, we may reduce the fraction by a common factor of 9 and we get a quarter. So that one is a quarter of the entire thing. What about part B? Part B is a 2 by 3 rectangle. Area of B is 2 times 3, which is equal to 6 units squared. No doubt we divide that by 36, which is the total area, to determine the fraction of the entire portion that is represented by B. So 6 divided by the area of the entire thing, which is 36, and we get 1/6. And it takes its position right there in the table. Anything else? A, B, do we go to C? Let's see what we do next. Yes, we move merrily on to C. And part C is a triangle whose perpendicular sides are 1 and 3 units. Area of a triangle, half base times height. That turns out to be a half times 1 times 3. So that is 3/2 units squared. And that we will divide by 36. Dividing by a number or fraction is equivalent to multiplying by its reciprocal. So we are taking opportunity here to use the reciprocal because we have 3/2, so we multiply that by 1/36, and of course we have what? Reduce this fraction by common factor of 3, so 3 into 36 is 12, 2 12s 24, so the fraction is 1/24. It takes its position also. Any more? Right, a rectangle G. We are gone all the way down to G. But it says complete the table, and we are completing the table. So the area of G, as we may say, A sub G is equal to, of course, G is a 1/2 rectangle. So the area of G is 1 multiplied by 2, and that is equal to 2 units squared. And of course, 2 divided by 36 is equal to 1/18. Do not forget that 36 is the total area, so we need to put the area of the one that we are concerned with over the area of the entire thing in order to determine the fraction that each one of those labeled share represents. What about D? D is a trapezium with parallel sides 2 and 3 units. And that is separated, those parallel sides are separated by a perpendicular distance of 3 units. So the parallel sides are 1, 2 units, 1, 2, 3 units, and we have 1, 2, 3 units. And of course, do not forget the formula for the area of a trapezium. The two parallel sides are added inside here, and the perpendicular distance between the two of them is divided by 2. So we have 2 plus 3 is 5. So we have 3, 5, 15 divided by 2. So 15 over 2 units squared. And we are going to divide that by 36 to find the fraction represented by 15 over 2 units squared. Do not forget that when we divide, we multiply by the reciprocal. So we will say 15 over 2 multiplied by 1 over 36. And of course, what do we know? 3 into 15 is 5. 3 into 36 is 12. 2 12s 24. So we will have 5 over 24. And it takes its position right there. Any other trapezium? Well, we only have trapezia left. So part E is a trapezium with parallel sides 1 and 3 units separated by a perpendicular distance of 2 units. So we have perpendicular distance between the two parallel sides. One parallel side, the other. So those 1, 2, 3, and this is 1 separated by 1, 2. So we have 2 over 2, and that is multiplied by 1 plus 3. So we have 4 here and 2 over 2. So we have 2 will cancel with 2 and only 4 is left. So we have 4 units squared. And divide that by 36, we get 1 over 9. Our final trapezium, part F, is a trapezium with parallel sides 2 and 4 units separated by a perpendicular distance of 2 units. So we have 1, 2, 3, 4. That's one of the parallel sides. And the other one that is parallel is 1, 2. So 2, 4, and separated by 2. So that should give us a round figure. So we have 2 divided by 2. 4 plus 2 is 6. And of course, these will cancel each other. So we will have 6 units squared. 6 divided by 36 is 1/6. There we have it. And we have completed the table. In order to move on to the next requirement, which is write the shapes in order of their perimeters. We are going to do some analysis to show that we can determine, for the most part, which one has a larger perimeter than the other without actually calculating it. So let's see how we are going to do that. We are going to do some analysis. Part B requires that we write the parts in order of the size of their perimeters. Calculating the perimeter of each shape is not impossible, but may prove to be too time consuming under examination condition to be realistic. So on this slide, I will put forward some arguments that will help in determining which shape has a larger area than the other without actually making calculations. And of course, this may be used in other branches of geometry in order to simplify analysis and probably even calculation. The shortest distance between 2 points is a straight line. Therefore, if we travel from A to B to C, we would have traveled a longer distance than if we traveled from A straight to C. So we have this A to C is shorter than going A to B, then B to C. So we go straight down instead of all the way around here, and that is shorter. So if a rectangle is cut in such a way that a trapezium is the result, the perimeter of the original rectangle is greater than the perimeter of the resulting trapezium. Right, because in the previous shape, we would have gone all the way to B and down, which is a longer distance. So if we can cut a trapezium from a rectangle, then the perimeter of the trapezium will be smaller than the perimeter of the rectangle, because shortest distance between 2 points is a straight line. And of course, this is going to be a straight line from A to C, whereas previously a longer route would have had to be taken. If we have a trapezium, the rectangle it was cut from has a greater perimeter than the trapezium. So if we can see the trapezium like this, and we can say, okay, then we would have cut it from a rectangle that goes like that. Then the trapezium is of a smaller perimeter than the rectangle that it was cut from. Because of the same reason, a triangle must have a smaller perimeter than the rectangle from which it was cut. So if we cut a triangle from a rectangle, the triangle will have a smaller perimeter, because we would have to go all the way here and down, which is a longer way than just going like that. So the remaining triangle will have a smaller perimeter than the original rectangle. Now, for convex polygons, if one can be enclosed in the other, then the one that is enclosed must have a smaller perimeter than the one enclosing it. So, since we have this 1, 2, 3, 4, 5, 6, six-sided figure, we have that hexagon inside of this rectangle or square. We are sure that the hexagon is of a smaller perimeter than the square or rectangle that we have right there. For the inner polygon, notice that the straight line goes from B to D. B to D. That distance is shorter than for the outer polygon that goes from B to A to D. B, A, D. So this BAD is longer if we put them together than this distance BD. Therefore, the outer polygon is of a greater perimeter than the inner one. This occurs 4 times in the arrangement. We therefore have no doubt that the inner hexagon has a smaller perimeter than the outer rectangle. A convex polygon is one whose sides will not go through it if we extend them. Hexagon and the rectangle will be shown to be convex on the next slide. Their sides will not go through them if the sides are extended. So these are convex. So this one is convex because we have extended all the sides. So notice that the sides of the hexagon are extended and none of them is passing through the polygon. So when we extend the sides of a convex polygon, none of the sides will pass through the polygon. The polygon is said to be convex. That one is also convex because when we extend the sides of that polygon, none of the sides passes through the rectangle that we have there. So that one is also convex. What about this one? On the other hand, at least one of the sides of a concave polygon will pass through it if we extend the sides. So we have extended the sides, see? And notice that 2 of the extended sides are passing through the polygon. Those 2, notice them? Those 2 are passing through. When we extend them, they are passing through the polygon, so that polygon is concave. The polygon is therefore concave. We have established that for convex polygons, the one that is contained in another is of a smaller perimeter than the one containing it. The same is not true for concave polygons. There we have a polygon of many sides inside of a rectangle. We do not imagine that the rectangle will have a larger perimeter than the polygon which it contains, because these number of sides that we have there, almost 1,000 sides that we have there, when we extend them, we are sure that it is going to be of a larger perimeter than the rectangle that is containing it. That is because the polygon that is contained in the rectangle is not convex. So because it is not convex, it is possible that being contained inside of that convex polygon, it will have a greater perimeter than the rectangle that is containing it. So because it is concave, it is possible that it will have a larger perimeter than the rectangle that is containing it. So we extend one side and we realize that the side is going through the figure. So an extended side of the polygon is passing through it. So we are sure that it is concave, not convex. One other premise of our argument is the hypotenuse is the longest side of a right-angled triangle. Most people know this, but it is quite noteworthy and might prove to be quite relevant in solving the problem. Let us take a look at the reason why the hypotenuse of a right-angled triangle must be the longest side. Therefore, it must be longer than the other two perpendicular sides. So there we have a right-angled triangle. All angles of a triangle add to give 180 degrees. The right angle is equal to 90 degrees. So the other two angles, of course 180 minus 90 is equal to 90. The other two angles must add to give 90 degrees. Each of them must therefore be less than 90 degrees. So let's just repeat that. All angles in a triangle add to give 180 degrees. One angle is 90. So if we subtract that from the entire thing, only 90 degrees will be left. And that 90 degrees must be shared between the other two angles. Therefore, it must be smaller. The resulting angles must be smaller than 90 degrees. So we are sure that each of them must be less than 90 degrees. The lengths of the side of a triangle are in proportion to the size of the angle that they are opposite to. The longest side is opposite to the largest angle, and the shortest side is opposite to the shortest angle. So that is our hypotenuse, which is the longest side. It is opposite to the right angle, which is the largest angle. We have established the fact that the right angle is the largest angle in the right angle triangle. It therefore must be opposite to the longest side, because the lengths of the sides of a triangle are in proportion or proportional to the size of the angles that they are opposite to. Our three facts will help us to solve the problem. A. For convex polygons, the one that is contained is of a smaller perimeter than the one containing it. And B. A trapezium is of a smaller perimeter than the rectangle from which it was cut. C. The hypotenuse is the longest side of a right angled triangle. So, by noting these facts, the amount of calculation that we will have to do in completing the next section is going to be very much smaller than otherwise. So, we are required to write the sides in the order of their perimeters, and of course we are putting the smallest one first. Obviously, the shapes with the smallest perimeter are C and G. All are convex polygons. G can fit into all others except C. Notice that G can fit into all of these except C. And C can fit into all others except G and E. So this one will be able to fit into all others except G and E. It therefore appears as if C has a larger perimeter than G because it can fit into less shapes than G. So C can fit into less shapes. So it appears as if it has a larger perimeter, but let's see if that is true. So let us compare the perimeters of the two polygons. So let us start 1 unit, 2 units, 3 units, 4 units. Good. Now at this stage, C has the hypotenuse of the right angle triangle and G has definitely 2 extra units. So we have the hypotenuse of this triangle and G has 2 extra units. So which one is greater? Up to this point, they are all equal. So which one is greater? So we have the 2 extra units there and we have the hypotenuse of the triangle there, not accounted for or not yet compared. Is the hypotenuse of the triangle greater than the 2 units? That is our question. Is this hypotenuse greater than the 2 units that we have there left for G? So remember that the hypotenuse is longer than each of the other 2 sides. So one of the sides is 3 units. 1, 2, 3 units. So one side is 3 units. The hypotenuse is therefore greater than 3 units and must be greater than the extra 2 units of G. So G has only another 2 units, but we have a hypotenuse of a right angle triangle that has what? One of the perpendicular side being 3 units. So we are sure that the hypotenuse is more than 3 units. So the perimeter of C is greater because this is greater than 3 and this is only an extra 2 units. The triangle C is therefore of greater perimeter than the rectangle G. So the smaller one goes first, G and then C after. E can fit inside of all of the other shapes. It is therefore the next in line. Now this one is E and we know that it can fit into all of these. As we can see, well, since it can fit into those, we know that for convex polygons that can fit into, its perimeter will be less than the perimeter of those that it fit into. Therefore, we are sure that E is of smaller perimeter than the remaining shapes. So E goes next. Now, the only real discrepancy that is left is between D and F. At first glance, D seems to have a greater perimeter than F. We can see at first glance, greater perimeter than F. It appears so. So at first glance, D seems to have a greater perimeter than F. And it does. But they may be closer in perimeter than is first apparent. Let us see if they are really closer in perimeter than at first apparent. So let us compare the perimeters. 1 units, 2 units, we are going 3 units, 4 units, 5 units, 6 units, 7 units, and 8 units. What do we know? We have 8 units compared, and the only parts that remain are the 2 diagonals here and here. So only the hypotenuses of the 2 right angled triangles are left, as we can see. Those are the 2 right angled triangles that we are considering. Let's show them again. Those are the 2 right angled triangles that we are considering. The hypotenuse of D is given by, we have 1, 2, 3 by 1. So the 2 perpendicular sides are 1, 3. So we have h is equal to the square root of 3 squared plus 1 squared. So h is equal to 9, the square root of 9 plus 1. So h is the square root of 10. So the hypotenuse of f is given by 1, 2, 1, 2. So we are sure h is equal to the square root of 2 squared plus 2 squared. So h is equal to the square root of 4 plus 4, which is equal to the square root of 8. Therefore, D will have the greater perimeter because the hypotenuse of this right angle triangle that is represented by this diagonal is greater than the hypotenuse of this right angle triangle that is represented by this diagonal. So we are sure that D is of a greater perimeter than F. So we will make our further analysis with that in mind. So it is clear that D will have a greater perimeter than F. Next, we will show that B has a smaller perimeter than F. So we are sure that this one has a greater perimeter than this. Now we need to show that this one has a smaller perimeter than this. We're just comparing these because, as a matter of fact, only that real comparison is left. So let us make that comparison. So we have 1, 2, 3, 4, 5, 6, 7, 8 units. So we have 8 units. And what is left? 2 extra units here, and the diagonal of this right here is left. And we know already from the previous slide what this will turn out to be. But we do not have to make use of that calculation at all. To complete the perimeters, B has another 2 units and F has the hypotenuse of the right angle triangle. Each of the perpendicular sides of the right angle triangle is equal to 2 units. The hypotenuse must always be larger than both those sides. It is therefore greater than 2 units, and F is therefore greater than B in perimeter. Of course, this is a hypotenuse of the right angle triangle that we have right there. And this we have 2 units, and this we have 2 units. The hypotenuse is always greater than the length of any of the other 2 sides. So we are sure that it is greater than 2. So this is only 2. So we are sure that the perimeter of this one is greater than the perimeter of that one. So B goes before F, and all we have left are A and D. D is a trapezium that may be cut from the rectangle, which is of course a square, A. So D is a trapezium that may be cut from the rectangle A. It is therefore of smaller perimeter than A, as we have discussed that the perimeter of a trapezium that may be cut from a square must be smaller, or be cut from a rectangle must be smaller than the perimeter of the rectangle from which it is cut. So we have D is smaller, A is larger, and the order is G, C, E, B, F, D, A in ascending order. It is said that the area of G is 2 square units. E, F, and G are arranged to form a trapezium, and we are required to tell the area of the trapezium in square units. Now G has an area of 2 square units. E, F, and G are arranged to form a trapezium. What is the area of the trapezium in square units? So all of those are going to form the trapezium. In Piaget's pre-operational stage, 2 to 7 years old, children learn that quantity remains the same even though the appearance may change. We need to apply this skill here, which is of course the skill that is required of a 2 to 7 year old. The total area does not change even though the shape changes. So we are going to convert this to a trapezium, but the area is going to remain the same. So we may use the same area that we have here, the area of a 3 by 4 rectangle, in finding the area of the resulting trapezium, because they are going to be the same. So according to the pre-operational stage, 2 to 7 years, children learn that quantity remains the same even though the appearance may change. So the area is going to be the same as this 3 by 4 rectangle that we have right there. And that is equal to 12 units squared, or 12 square units. Now, the shapes will be rearranged to form a trapezium, because we need to also show how the shapes may be arranged to form a trapezium. Need to sketch the trapezium, clearly showing the outline of each of the 3 parts. That's not difficult on computer. So there we have the trapezium. Here we have two functions defined as g of x is equal to 2x plus 1 divided by 5, and f of x is x plus 4. Calculate the value of g of negative 2. Now to find g of negative 2, in the function g, where we see x, we put negative 2. So we have g of negative 2 is 2 times negative 2 plus 1 divided by 5. So we have 2 times negative 2, that is negative 4 plus 1, negative 3 over 5, when that is simplified. Next, we are required to find g of f of x. To find g of f of x, in the function g, where we see x, we put f. So g of f is equal to 2 times f plus 1 over 5. 2 times f plus 1 over 5. So let's do that. And of course, we have taken this step because the CSEC report says that when students are composing functions, the common mistake that they make is they substitute the wrong function into the other. So we start off by saying g of f. So we say g of x is equal to 2x plus 1 over 5. So g of f is 2f plus 1 over 5. And that is what we have right here. We further substitute the algebraic expression for f right here. So the algebraic expression of f will go right here. So we will have, what is f? X plus 4. So where we see f, we replace that with f plus 4. So 2 times x plus 4 plus 1 over 5. And that is simplified to give 2x plus 9 over 5. Continuing, find the inverse of g of x. Find the inverse function g inverse of x. So let us continue. So to find g inverse of x, replace g of x with x and x with g inverse of x. And that is what we are going to do. Now, for these functions, we may just look at them and write down the inverse in the following way. We are looking at the arithmetic operation that composes the function. So, first, we multiply by 2, then add 1, then divide by 5. To find the inverse of g, we will find the inverse of each operation and we will perform them in the reverse order. So g inverse of x will be 5x minus 1 divided by 2. So we say 2x plus 1 over 5. So we go in the opposite direction and we are doing the opposite of each operation. So whereas we said 2x plus 1 divided by 5, we will say multiply by 5. So we'll have 5x, then we subtract 1, and then we divide by 2. So g inverse of x will be 5x minus 1 all over 2. But we may use transposition of formula to arrive at our answer. So, where we see g of x, we replace that with x. And where we see x, we replace that with g inverse. So, by transposition we are dividing by 5 here. We multiply both sides by 5, in which event 5 will be eliminated from the denominator right here, and we will have x multiplied by 5. So we'll have 5x. Next, we need to eliminate this positive 1. Of course, we need to eliminate this positive 1 and this 2. But we are going to eliminate first the one that is least related to the function g. And that is this positive 1. That we will do by subtracting 1 from both sides. The 1 will be eliminated on this side, and we will have 5x minus 1 on the other side. Finally, 2 g inverse means 2 multiplied by g inverse, so we will divide both sides by 2. The 2 is going to be eliminated from this right hand side, and on the left hand side we will have 5x minus 1 divided by 2. So we may use transposition of formulae, although this function is one that does not really require the process. I'm just including the process here just in case a student may want to turn to this method in order to solve a similar problem. So g inverse of x is equal to 5x minus 1 all over 2. Of course, we may find the inverse of functions as simple as this one that we have right there in one step, as we have demonstrated before carrying out this process. The length of the rectangle is 2x minus 1 centimeters, and the width is x plus 3 centimeters. So, write an expression in the form ax squared plus bx plus c for the area of the rectangle. That means we are going to write it in the form of a trinomial in x squared, or trinomial in x. That we will do by finding the area, and of course the area is equal to the product of the length and the width. So we multiply those by area is equal to length by width. So what do? We take 2x and we multiply that by x, and we get 2x squared. Then we take the 2x, multiply that by 3, we end up with 6x. Multiply negative 1 by x, because we have exhausted the 2x, so we move on to the negative 1. So the negative 1 is used to multiply the x, and we get negative x. And then we have what? Negative 1 multiplied by 3, and that is equal to negative 3. Now we have two like terms, and the like terms are combined by adding the coefficients. The coefficient here is 6, and the coefficient here is negative 1. 6 added to negative 1 will give a positive 5. So positive 5 is the coefficient of the new middle term. So the middle term will be 6x minus x, which is 5x. And that completes the expression of our area written in the form of a trinomial. Given that the area of the rectangle is 294 centimeters squared, determine the value of x. And the expression that we have here, that is the expression of the area that we will equate to 294. Then we will solve that equation by first getting all the non-zero terms on the left hand side, and the right hand side will be occupied by 0. So we need to subtract 294 from both sides, in which event the 294 will be eliminated from this side, and we will have a negative 297 on that side. Now we need to factorize the trinomial. We are going to be using the method of factorization in the solution. So we need to determine the two numbers that multiply to give 2 times 297, and when we add them, the result is a positive 5. Now 297, if we break that down in its product of prime factors, this is what we will get. And do not forget that we have a 2 right there. So the prime factors will be 2 times 3 times 3 times 3 times 11. And from that, we will get a pair. When we add them, we get a positive 5. When we multiply them, we get the same thing as 2 times 297. We do not need to determine that product because we have it here in terms of prime factors. And of course, since we are multiplying a positive by a negative, one of the number will be positive and the other will be negative. So we have those two numbers, 3 times 3 times 3, so that is 27, and 2 times 11, that is 22. So it is a positive 27 and a negative 22. So the two numbers are negative 22 and positive 27, and we are going to factorize the resulting quadratic expression by grouping. So we will take a common factor of 2 here, and of course we will take a common factor of 27 here. Of course, we can see here 2 plus 7 is equal to 9. Now if we have a number that is like that, where when we add the two end numbers, we get the one in the middle, we know that it is a multiple of 11. And we know that if we divide this by 11, we will get 2 and 7. So we'll get 27. So 2 plus 7 is 9. So we have 297. Because the two end numbers are to give the middle, we are sure that it is a multiple of 11. And we know if we divide it by 11, we will get the two end numbers. So that is something that we can make use of very quickly. So we have the factors are there. 2x common, x minus 11 right there, and of course 27 is common in these two, and x minus 11. Then x minus 11 is 1 and 2x plus 27 is the other. Solving the linear equation, of course, when we eliminate the negative 11 to the other side of the equation, we have a positive 11. And when we eliminate this 27 to the other side, we get a negative 27, but we will have to divide by 2. So we'll get 27 and negative 27 divided by 2, and that will give negative 13.5. However, a dimension of a rectangle cannot be negative, so we have to choose the positive value only. So L is equal to 2x minus 1, and L is 11. 2 times 11 minus 1, 22 minus 1. That will give us 21. So 21 centimeters for the length, and let's see what we have for the width. 11 plus 3. X is equal to 11, and we have x plus 3, that is equal to 11 plus 3, and that will turn out to be 14. A company manufactures gold and silver stars to be used as party decorations. The stars are placed in packets so that each packet contains X gold stars and Y silver stars. And of course, the first condition that we have is already described. So we have the inequality and we have the description. It says each packet must have at least 20 gold stars. And of course, we have X is greater than or equal to 20. Then we are required to write the inequalities to represent the other conditions that we have there not described or not represented by an inequality. So we have each packet must have at least 15 silver stars. At least 15 means 15 or more. So Y is greater than or equal to 15. The other one is the total number of stars in each packet must not be more than 60. So the total must not be more than 60. It must be less than or equal to 60. B. Describe in words the condition represented by the inequality X is less than 2Y. So we have X is less than 2Y. X is the number of gold stars and Y is the number of silver stars. X is less than 2Y means the number of gold stars is less than twice the number of silver stars. We are now about to graph the inequalities. But before doing so, we need to be settled as to the specifics of some of the lines that we will draw. So, X plus Y is less than or equal to 60. The line corresponding to this inequality is X plus Y is equal to 60. If the sum of two numbers is 60 and one is 0, then the other one is 60. Because the sum must be equal to 60, one is 0, so the other must be 60. And it is true irrespective of which one we use, X equals 0 or Y is equal to 0. Therefore, if X is equal to 0, then Y is equal to 60. And if Y is equal to 0, then X is equal to 60. The line will pass through the points 0, 60 and 60, 0. What about that one? The associated line is a favorite of CSEC. As explained in volume 3 of Richard James Mathematics Resources, which is R²JM, it may come in many guises. So, as it is explained in Richard James Mathematics Resources, volume 3, that same line may come in many guises. Let us use transposition to write its associated equation in a more familiar form. So let us transpose that. We have, well, we are not actually transposing this. We are transposing the equation of the line that is associated with the inequality. So the line that is associated with the inequality is X is equal to 2Y. And we are going to transpose that one. So we have exchanging sides, 2Y is equal to X. And of course, dividing both sides by 2, the 2 is going to be eliminated from the left-hand side. And we have Y is equal to X divided by 2. And that is a line that we are familiar with. The equation may also be written Y is equal to a half of X. This means that whatever the value of X is, Y is half of it. Y is equal to a half of X. So, if X is equal to 60, Y is equal to a half of 60, which is equal to 30. If X is equal to 40, Y is equal to a half of 40, which is equal to 20. When X is equal to 0, a half of 0 is 0. The line will therefore pass through 60, 30, so the X is 60, the Y is half of it, the X is 40, the Y is half of it, and also through the origin that has equation 0, 0. The line x is equal to 20 is a vertical line that crosses the x-axis at 20. So, no problem with that one. The line y is equal to 15 is a horizontal line that crosses the y-axis at 15. The line that has equation x plus y equals 60 will pass through the points 60, 0 and 0, 60. So 60, 0, we will go 60 for the x and no movement in the y direction. It will be right there. And 0, 60 is the other one. It will have x ordinate equals 0, no movement in the x direction, but it will go up to 60 and the line will go through those 2 points. The line y is equal to a half of x passes through 60, 30. Let's plot that one. 40, 20 there, and also through the origin 0, 0. Of course, it is a dotted line because the inequality says x is less than 2y, and we transpose that to y is greater than a half of x. So it is not a greater than or equal to. Therefore, the line will be a dotted line, and values of x and y on that line are not applicable, since for the inequality it must be greater than. So y must be not equal to, must be greater than a half of x. According to the inequality, y is greater than a half of x. So y is strictly greater than a half of x. The broken line is an indication of this. Part D. The packets of stars were selected for inspection. Their contents are shown below, and that is where we have them in that table. Plot the points A, B, and C on your graph, hence determine which of the 3 packets satisfy all the conditions. Does that one? 25 gold stars and 20 silver stars. Of course. There we have it. A is inside of the region bounded by all of the inequalities. It satisfies all of the conditions. What about 35 to 15? 35 go up to 15. No. It is not in the region because it is below that dotted line when y is greater than a half of x. It has to be above that dotted line to satisfy at least this one that we have right here. So we are sure that it does not satisfy the inequality. B does not satisfy all of the conditions. It is outside of the region bounded by all of the inequalities. What about that one? 30 and then goes up to 25. Right, so C is inside of the region bounded by all of the inequalities. It satisfies all of the conditions. Let's have some fun. So, we are given sine theta and we need to express in fraction or third form cos theta and tan theta. So, we are dealing with trig ratios. Trig ratios are directly applicable to right-angled triangles. There is our right-angled triangle. So we are told that sine of theta is the square root of 3 over 2. And of course, what is sine equal to? Opposite over hypotenuse. And that is the square root of 3 over 2. So call one of the acute angles theta. We call that one theta. So that is the one whose sine is square root of 3 over 2. That means the side opposite to this angle is square root of 3 and the hypotenuse is 2. So the longest side is the hypotenuse. Name the other side relative to the given angle. So that is the hypotenuse relative to the given angle. The other side that we have there, this one is opposite to the angle, because we need opposite, because we are talking about sine, which is opposite over hypotenuse. Of course, the adjacent side is also given, which is the one alongside the given angle. So this side is opposite to the given angle, and this side is adjacent to that angle that is specified right there. So, of course, we have sine theta is square root of 3 over 2. So the hypotenuse is 2, and the side opposite to the angle is equal to the square root of 3. And there we have them. Use Pythagoras' theorem to find the length of the short side of a right angled triangle. So, of course, we need to determine the length of this one. So, the length of one short side, do not forget how the formula of the basic representation of Pythagoras' theorem was transposed to give the length of one short side, which is the square root of the hypotenuse squared minus the square of the other known one, or the other short side. So, we will replace the hypotenuse squared with 2 squared, and of course the square of the other side is the square root of 3. So we will square that. This results in 2 squared is 4, and the square root of 3 is 3. So we have a is equal to the square root of 1, and that is equal to 1. So find cos theta. Cos theta is adjacent over hypotenuse. So adjacent over hypotenuse, adjacent over hypotenuse. So cos theta is equal to 1. Tan theta is opposite over adjacent. The opposite is square root of 3, and the adjacent is 1. The square root of 3 over 1 is equal to square root of 3. Next, we will determine the value of sine theta over tan theta. And of course, sine theta over tan theta just means sine theta divided by tan theta. What is sine theta? We know it here from the original statement of the problem, square root of 3 over 2. And what is tan theta? Tan theta is equal to square root of 3. So, square root of 3 over 2 divided by the square root of 3, and that is equal to a half. In this question, take pi equals 3.14 and r is equal to, which is the radius of the earth, 6,370 kilometers. The diagram below, not drawn to scale, shows a sketch of the earth with the north and south poles labeled N and S respectively. The circle of latitude 37 degrees north is also shown. Calculate to the nearest kilometer the length of the circle of latitude 37 degrees north. So, the length of the circle of latitude. So, according to module 1, the radius of a circle of latitude is given by Re cos theta. Of course, Re is the radius of the earth and cos theta is the angle of latitude. So we will use this in our formula in finding the circumference of the circle. So we have C is equal to 2 pi r. We know pi is already 3.14 and r is the radius of the circle of latitude, which is the radius of the earth times cosine of the angle of latitude. So the length of the circle of latitude will be 2 times 3.14 times the radius of the earth times cosine of the angle of latitude. Now, pi is 3.14. The radius of the earth is 6,370 kilometers, and theta, which is the angle of latitude, is 37 degrees. So that is our expression. When that is simplified, we get 31,948 kilometers. Next, two towns A and B have coordinates 37 degrees north and 50 degrees west, and 37 degrees north and x degrees east. So both of them are on the same circle of latitude 37 degrees, whose length we have found, or circumference we have found. So A is 37 degrees north, 50 degrees west. B is 37 degrees north, x degrees east. We have the circumference of a circle and the length of an arc of it. So we know the length of the arc because it says so right in the statement of the problem. And of course it says that the distance is 5,390 kilometers. That's the distance between the two of them. Right, so we need to find the angle associated with the fraction of the circle or the arc of the circle. And of course we may make use of the formula that what? The length of an arc of a circle is equal to the fraction associated with the arc multiplied by the circumference of the circle. And how do we know the fraction? The fraction will be the angular representative of the arc divided by the angular representative of an entire revolution, which is 360 degrees, and that we will multiply by the circumference of the circle. The result is 5,390 as we have it right there. So by simple transposition, we have multiplying both sides by 360 degrees, and then of course dividing both sides by 31,948, and this is the result that we have. Simplifying that, we have theta is equal to 61 degrees, and we are required to find x, which is the longitude of the point B, and of course B is located east of the Greenwich meridian. So the points are on opposite sides of the Greenwich meridian, and of course this one is on a longitude of 50 degrees west and the other is x degrees east. So those two angles will have a sum of 61 degrees. See, 50 here and x there. So the total angle will be 61 degrees. Therefore, x plus 51 is equal to 61. Do our simple subtraction. X is equal to 11 degrees. The figure is a regular octagon with center x, and xy is equal to 6 centimeters. So the figure is a regular octagon. All sides are equal for regular figures, and xy is equal to 6 centimeters right there. we need to calculate the size of the angle YXZ. 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 So this angle that is right there as shown. We know that we have the entire angle of a revolution is 360 degrees, and of course it is going to be divided into 8 parts. So each one will be 360 divided by 8, and that is equal to 45 degrees. So the angle YXZ is the angle associated with 1/8 of a revolution. So let us put that 45 degrees there as a reminder, just in case we will need it in calculating something else. The area of triangle XYZ is the next thing that we need to calculate. The area of triangle XYZ. The area of any triangle may be found by taking half of the product of any two sides and multiplying the result by sine of the angle that the two sides form. So if we have a triangle as we have right there, the area of this triangle may be found by taking half of the product of any two sides. Now from here to here we have 6 centimeters. No doubt we have another 6 centimeters here. This is the center. And of course we have the angle that the two sides form. So the angle is 45 degrees. So we may use that formula, half of the product of any two sides multiplied by the sine of the angle that the two sides form, and we have a half of 6 times 6 times sine of 45, which is equal to a half of 6 times 6 times 0.7. And let's see what that turns out to be. That turns out to be 12.7 centimeters squared. So let us make a little rough check to see if 12.7 centimeters squared is a possibility. So we have 0.707, that is what sine of 45 is. So half of 6 is 3. 3 times 6 is 18. And then we are going to take 0.707 of 18, which is round about 3/4 of 18. So 3/4 of 18 is approximately 12.7 centimeters squared. So a rough check shows that 12.7 centimeters squared is a quite possible answer. And of course it's the answer that we got with the calculator, but sometimes students get an answer with the calculator after making a mistake, and they do not realize that a mistake was made. The octagon is made up of 8 identical triangles. Its area is therefore 8 times the area of each triangle. So we need to find the area of the entire octagon, and that is easy because it is made up of 8 identical triangles. The area of each is known. So we just multiply the area of one by 8 and we get 101.6 centimeters squared. In the diagram, we are required to find certain angles. One is TPQ. That's the first one. The angle that is subtended by a diameter is a right angle. So TPQ is a right angle because it is subtended by this diameter. So we are sure that it is equal to 90 degrees. What about MTQ? A tangent and a radius meet at right angles. So MTQ, the tangent meets the radius or diameter at right angles. So we are sure that MTQ is equal to 90 degrees. What about TQS? TQS. The angle that the tangent makes with the chord is equal to the angle that the chord subtends at the circumference. So the angle that the tangent, this is the tangent making an angle with the chord, it is equal to the angle that the chord subtends. So this is the chord and this is the angle that it subtends at the circumference. So they are both equal. So TQS is also equal to 23 degrees. Now SRQ. SRQ. Of course, SRQ is in the cyclic quad. So opposite angles of a cyclic quad are supplementary. They add to give 180 degrees. Those two. But we will not go straight into using that principle. We need to find this angle right here. So STQ, which is STQ, this angle right here, is a part of this right angle that we have right here, of which we know the 23 degrees that we have there. So the 23 degrees, that angle is already known. Therefore, we may determine the angle that we have by subtracting 23 from 90. So that angle is 90 minus 23, which is equal to 67 degrees. We will proceed to determine now the angle SRQ. So SRQ is in a cyclic quadrilateral. Notice that we have a four-sided figure in this half of the circle. So we are going to say now, four-sided figure, of course, all vertices are touching the circumference of the circle. So we know that it is a cyclic quadrilateral. So it is safe to say we are using the fact that the opposite angles of a cyclic quad are supplementary. They add to give 180 degrees. So SRQ is 180 degrees minus 67, and that is equal to 113 degrees. OK and OM are position vectors such that OK is equal to K and OM is equal to M, as we have them right there. So sketch a diagram showing the approximate positions of points R and S such that R is the midpoint of OK, S is the midpoint of OM, okay? S is the point on OM such that OS is equal to 1/3 of OM. So let us go straight ahead. R is the midpoint of OK, and OS is 1/3 of OM. So 1/3 the way from O to M, we have S right there. And we need to determine the following vectors. As a matter of fact, it says write down. Not all of them will be possible to just write down, but we can write down the initial representation of the vector, and then we may simplify the result. So let us go for MK. From M to K, we go opposite to M, the vector M, and in the positive direction of K. So we go opposite to M, minus M, and positive K. So MK is equal to K minus M. Then RM. What do we do for RM? A half of K. So negative a half of K, we are actually going in the opposite direction too. So negative a half of K plus M. So putting the positive one at the front, we have M minus a half of K. So determine Ks. What is Ks? From K to S, all of K minus K going in the opposite direction, minus K going in the opposite direction. So negative K plus, how far do we go to S? to 1/3 of m. So minus k plus 1/3 of m, and we have, putting the positive one at the front, a third of m minus k. Then rs, going a half of k and a third of m. So in the opposite direction too, so we go negative k plus 1/3. We have a negative half of k and a positive 1/3 of m. So turning them around, positive at the front, we have 1/3 of m minus 1/2 of k. L is the midpoint of Rm. So we are going to put that up there. L is the midpoint of Rm. There we have L. Use a vector method. Prove that Rs is parallel to KL. Rs is parallel to KL. Where's Rs? Here it is. Rs is parallel to KL. Okay. So we have Rs right here. So we need to find KL. From K to L we have a horrible situation. So we are going to have what? KR plus RL. KR plus RL. What is KR? KR is a half of K going in the opposite direction. So KR is negative a half of K. Right, so we have KR here is a negative a half of K. And what is RL? RL is a half of RM. So a half of, let us find RM. This is RM. So we have negative a half of K plus RL. So we have negative a half of K plus RL. And of course, RL is a half of RM. So RL is a half of RM. So RM is what we have right here, m minus a half K. So putting that together. So we have KL is equal to, when we simplify that, we have here a half of K, and we have a half of K. So that is going to be minus a half of K and minus a quarter of K. Both are negatives, so we put them together and have one big negative. When we add numbers that have the same sign, we combine the values and the answer will have the same sign as the numbers that we have added. So we have added a negative a half with a negative a quarter, and the answer is negative 3/4. And of course, a half of m is the only term in m that we have. It goes back right there. Now, by analysis, we realize that 3/2 of Rs is equal to 3/2. Where is Rs? Here we have it. That is Rs. So 3/2 of Rs is equal to 3/2 of a third of m minus a half of k. And that simplifies to give a half of m minus 3/4 of k. What do we know? There we have them then. We have 3/2 of Rs is actually equal to KL. So 3/2 of Rs is equal to KL. If one vector is a scalar product of the other, then they are parallel. And of course, it is not going to be difficult for a candidate to realize that I use very harsh or even drastic measures in arriving at the expression that we have there, taking 3/2 Rs and showing that is equal to KL. But it is necessary to show that one vector is a scalar product of the other, and if so be the case, they are parallel. There we have, for number 14, 3 matrices, and we are going to have a lovely time making simple calculations. So the first thing that we will find is 3a. So A is this matrix, 3 times that. All we do is multiply each one of these terms by 3, and that's all there is to it. Then we are about to find B inverse, and there we have it. What about B inverse? 1 over the determinant 5, 2 minus 3, 3. So 1 over the determinant 5, 2 minus 3, 3 multiplied by the adjoint. The adjoint is what we get when we change the signs of these two and change the positions of these two. The fraction reduces or simplifies to, it simplifies to 1 over 1, which is equal to 1. So B inverse is actually equal to 2 negative 3 negative 3, 5. Thirdly, we need to find 3a plus B inverse. No problem. Here we have 3a and here we have B inverse. So when we add them, what do we know? Cannot add 2 matrices unless they are of the same order. Both of them are 2 by 2. We may add them. When we add matrices of the same order, we add corresponding elements. So let's do that. So we are going to say 3a plus 2, 3b minus 3, 3c minus 3, and 3d plus 5. And that is what 3a plus b inverse will be equal to. Part 4. The values of a, b, c, and d will be determined if 3a plus b inverse is equal to c. So we have what? 3a plus b inverse, and that we will equate to c. So this is 3a plus b inverse, and we need to equate that to c. So what do we know? This is 3a plus b inverse, and this is c that we take from right there. And we need to determine all of those unknowns. A, 3a plus 2 is equal to 14. Minus 2 from both sides, we get 3a is equal to 12. Dividing both sides by 3, we get a is equal to 4. Then 3b minus 3 is equal to 0. So 3b minus 3 is equal to 0. Adding 3 to both sides, we have 3b is equal to 3. Then dividing both sides by 3, we get b is equal to 1. Then 3c minus 3 is equal to negative 9. Adding 3 to both sides, we have 3c is equal to negative 6, and c is equal to negative 2. Finally, 3d plus 5 is equal to 5. Subtracting 5 from both sides, we get 3d is equal to 0. And of course, dividing both sides by 3, we get d is equal to 0. In the diagram, a parallelogram EFGW and its images after undergoing 2 successive transformations are shown. So we are going to describe in words the geometric transformations J, which maps EFGH to E prime, F prime, G prime, H prime. So the one that maps this one to this one. Notice that what? That one goes right down there. So we are sure J is a translation by 4 units in the negative y direction. So K is a rotation through 180 degrees about the origin. And of course, K is the transformation which maps this one to this one. So maps E prime, F prime, G prime, H prime to the double primes. And of course, if we take a look, we notice that E prime goes straight through here, straight line through the origin, and of course, H prime goes straight to the origin to H double prime. So when that happens, we are sure that the transformation is a rotation, and because of the position, it is quite clear that it is a rotation through 180 degrees about the origin. So, write the matrix which represents the transformation described above as J. J has matrix 0, -4. The matrix of transformation of a translation is a column matrix that is generally added to the point that we transform. And K, we need to write down the matrix of a rotation by 180 degrees about the origin. Richard James Mathematics Resources will clarify that, but some students have it in memory, some will have to work it out. The working out of it is shown in Richard James Mathematics Resources. So we may write that down. K has matrix -1, 0, 0, -1. The point P, 6, 2 is mapped onto P prime by the transformation J. State the coordinates of P prime. Of course, if it is by J, we know that J is going to be added, that vector is going to be added to the point. So we have this P in a column vector form 6, 2 to be added to the vector of transformation 0, -4. So we have 6 plus 0 is 6, and 2 plus -4 is -2. And what did it say? State the coordinates of P prime. So we need to give the information in coordinate form. We cannot leave it as it is because it is not in coordinate form as it is. The statement of the problem requires coordinate form, so we have to write that in coordinate form. Next, we need to transform the point P, 5, -4, onto its image Q prime by the transformation K. And of course, all other matrices of transformation, with the exception of translations, are 2 by 2 matrices that are multiplied by the points to be transformed. So we will multiply Q by the matrix of transformation, and Q prime will therefore be equal to the product of the matrix of transformation, rotation through 180 degrees about the origin. We are going to multiply that by the coordinates of Q represented in column matrix form, and the result is given as Q prime -5, 4.